Okay, so what I'm going to be comparing here is the difference between tensile strain, lateral strain, and then using these both for Poisson's ratio. Okay, so say if I had like a specimen of a material, say a metal bar, as usual, and I'm applying my force on it, we know that it's going to experience like strain or a deformation on like on both sides. It's going to be stretched. So I can say that this amount is say this amount is going to be the change in length divided by 2. So half of it is going to go up and half of it is going to go on the bottom. Yeah. But since this object has a fixed volume, it must necessarily get thinner. So you will see it have a thinner, longer shape. And so now so it's going to also get thinner as well. So I can talk about things in terms of a lengthwise strain, but I can also have a widthwise strain. So this amount is, I'll call this, I'll call this delta W instead. So I can call this delta W on 2, and I can call this also delta W on 2. Yeah. So instead of having strain, just the original strain, which is a change in length over the original length, I can also have a lateral strain, which is the change in width over the original width. So the diameter or width. Diameter for a cylindrical shape, width just for a rectangle. Yeah. So the ratio of the tensile and lateral strains is what we call our Poisson's ratio. As a little cute V. And it's literally the negative of EL over L. Or I could call this ET. Tensile because you're pulling. Lateral means sideways. There's a negative here because the change in width is negative. It's going to go from a bigger width to a smaller width. So that's why we have a negative over here, to have a nice, wholesome, positive ratio. Yeah. The reason why I'm telling you all of this is because often they'll give you 2 of these 3 pieces of information, and you'll have to solve the next one. So, yeah. And so you have to solve the next one so that you can continue into like the rest of the working. So it's like an extra step into your working.